Igor Ivanovich Sikorsky, who lived from 1889 to 1972, gained fame during the First World War for creating a unique fleet of airplanes. He was the one who built the world's first series-produced multi-engine aircraft, the giant bombers known as Ilya Muromets. But aside from these giants, Sikorsky also designed light aircraft of various types, primarily fighters. Interestingly, his first experimental models did not appear as fighters. Their creation was a result of the designer's success in developing light two-seat reconnaissance planes. Igor Ivanovich Sikorsky's two-seat biplanes won international military aircraft competitions held by the Russian War Department in 1912 and 1913. At the 1913 competition, Sikorsky's monoplane also took second place. If, due to a poor understanding of the future needs of military aviation, the order for his first aircraft was limited to only 2 machines, the situation with the procurement of the 1913 competition winners was quite different. In 1913, the Russian government adopted the Great Program for Strengthening the Army. According to this program, dozens of aviation detachments were to be formed: Corps, Fortress, Field, Army, and special units for Cavalry Corps. The main task of these detachments was to carry out reconnaissance. For the maneuverable corps detachments, the plan was to build light and compact monoplanes, while for stationary fortress and field detachments, heavier biplanes. In June of 1914, the Russo-Baltic Wagon Factory joint stock company, where Igor Ivanovich Sikorsky worked as the chief designer and head of the aviation department, signed a contract with the main military technical directorate of the War Ministry. The contract stipulated that by the end of the year, 45 airplanes were to be built: 14 reconnaissance biplanes, 24 reconnaissance monoplanes, 2 training monoplanes, and 5 training biplanes. The order was quite large for that time, and could have been even greater if the department had not been busy with serial production of the multi-engine Muromets. At the same time, the Naval Ministry of the Russian Empire adopted its own Great Program for Strengthening the Navy, which also paid great attention to the development of aviation. It envisioned the creation of a number of aviation stations equipped with new seaplanes, including float versions of biplanes. For these new aircraft, new pilots had to be trained, and on September 1, 1914, the ministry signed a contract with the factory to build a light training float plane called Malyutka, designed by Igor Ivanovich Sikorsky. Previously, naval aviation had used a small float plane as a training aircraft. For the training of land-based pilots, Igor Ivanovich Sikorsky built the biplane Malyutka. Both aircraft were almost identical in design, differing only in the placement of pilot seats. On the naval version, the seats were arranged one behind the other, while on the land version, side by side. Following the example of these well-proven aircraft, it was planned to build both the 5 training biplanes ordered by the War Department and the training Malyutka for the Navy. However, both prototypes had been built as early as 1912 and had already become morally outdated. A fundamentally new single- or 2-seat fast-training biplane was required. The board of the Russian-Baltic Wagon Factory joint stock company, particularly its chairman, the prominent organizer of Russian engineering, Mikhail Vladimirovich Shidlovsky, decided to entrust Igor Ivanovich Sikorsky with the development of a light aircraft that would meet the new requirements. Since the chief designer was primarily occupied with the creation of heavy multi-engine giants, supervision over the construction and testing of light aircraft was usually entrusted to one of his closest associates. In modern terms, leading designers were appointed, individuals who were also test pilots for their own machines. The godfather of the S-16 aircraft was Lieutenant Georgy Ivanovich Lavrov of the Russian Navy, a childhood friend and loyal companion of Igor Ivanovich Sikorsky. An experienced and courageous pilot, he was also a talented inventor with a deep understanding of aviation technology. Igor Ivanovich Sikorsky's main assistant in aircraft design was his colleague from the Kyiv Aeronautics Society, Anatoly Anatolyevich Serebrennikov. He headed the technical bureau of the aviation department at the factory. Sikorsky prepared only the general sketches, layouts, weight calculations, and drawings of some key parts of the new aircraft. Based on these blueprints, his co-workers, usually draftsmen with a mid-level technical education, produced detailed working drawings of these components. Aerodynamic studies of the new machine were conducted both by Sikorsky himself in a small factory laboratory and, at his request, under the direction of Vasily Adrianovich Slesarev, at the largest aerodynamic laboratory in Russia, the one at the St. Petersburg Polytechnic Institute. The S-16 project was developed by Igor Ivanovich Sikorsky in October 1914. To some extent, its prototype during the design phase was the tabloid aircraft of British designer Thomas Sopwith, which at the time had gained fame in international competitions for its excellent speed performance. The military of many countries became interested in aircraft of this type, planning to use them as cavalry planes. Small, fast machines that, like mounted scouts, could suddenly appear near enemy positions, conduct reconnaissance, and quickly deliver gathered data to their command. Between 1914 and 1915, many aircraft of the tabloid type were built in various countries. In Great Britain, they were known as Scouts. However, due to their limited payload capacity, these small planes did not achieve great success as reconnaissance aircraft. Instead, they became the foundation for an entire class of single-seat fighter biplanes that lasted up to the Second World War. By analogy with most Scouts, the S-16 adopted the general scheme of a clean biplane, along with the main parameters and a layout featuring two pilot seats, positioned closely together in a compact cockpit. Yet the structure of the S-16's parts and details was developed by Igor Ivanovich Sikorsky based on his own experience in aircraft construction, primarily that of light biplanes. Unlike the tabloid, lateral control in the S-16 was achieved, as on all Sikorsky aircraft, with ailerons rather than wing warping. The engine mounting and cowling were also designed differently, among other elements. Construction of 3 experimental S-16 aircraft began in the workshops of the aviation department of the Petrograd factory in November 1914. The first one was completed in January 1915. The Russian Naval Department, which had commissioned the Baby and had always supported Igor Ivanovich Sikorsky's work, allocated for the aircraft a Roan engine producing 80 horsepower and helped transport it to Revel, now Tallinn, where Georgy Ivanovich Lavrov was serving at the time. However, immediate testing of the S-16 proved impossible. In February, the airfield was covered with deep snow, and the aircraft was not equipped with skis. With the outbreak of the First World War, the production order for Igor Ivanovich Sikorsky's light aircraft was suddenly jeopardized. Deliveries from France were disrupted, and domestic aircraft engine factories did not produce the 100-horsepower Gnome monosoupape engines for which previous models had been designed. In November of 1914, the plant's management appealed to the War Department with a proposal to replace the ordered aircraft with an equivalent number of new models designed for 80-horsepower Gnome engines manufactured by the Moscow branch of the French company. At that time, a major event occurred in Russian aviation that deeply influenced the work of the Russo-Baltic Aeronautics Department and the creative activity of Igor Ivanovich Sikorsky. In December of 1914, by order of Emperor Nicholas II, the squadron of airships was established, the first strategic aviation unit in the world. At the Yablonna station, north of Warsaw, all-built heavy bombers, Ilya Muromets, were assembled. The squadron was led by Mikhail Vladimirovich Shidlovsky, chairman of the Russo-Baltic Company Board. Igor Ivanovich Sikorsky accompanied him to Yablonna. To create an effective combat unit and ensure the operation of the heavy aircraft, they began gathering into the squadron all the light aircraft produced by Russo-Baltic from various fronts, along with the pilots capable of flying them. In March of 1915, Georgy Ivanovich Lavrov was called from the naval fleet. Shortly after, one of the experimental aircraft was sent from Reval, without its engine, which had been returned to the Naval Department. Almost simultaneously, Mikhail Vladimirovich Shidlovsky ordered the Aeronautics Department to send 2 more experimental aircraft to Yablonna. The machines were dispatched to the squadron on the 6th and 19th of March, together with the Ilya Muromets bombers and other light aircraft. They arrived like the first aircraft without engines. The 2 additional aircraft differed from the first in their wing design. While the first had slightly swept wings, the other 2 had straight wings with a larger dihedral angle. The wingspan of all the aircraft was roughly the same. In addition, the engine cowlings had distinctive streamlined fairings. The engine famine was an incurable disease that plagued Igor Ivanovich Sikorsky throughout the entire First World War. While the problem of engines for heavy bombers was largely resolved by the end of 1916, for Sikorsky's light aircraft the lack of suitable motors proved to be an unsolvable issue. For the first 3 aircraft, engines were eventually obtained. They were taken from a batch sent from central depots for the French training aircraft delivered to the squadron's school in early 1915. The first 2 planes were equipped with Gnome engines producing 80 horsepower, and for the third, one of the first Russian-made Kalep engines producing 60 horsepower was acquired. The lower power compared to the Gnomes and Ronus originally intended forced a redesign of the third aircraft. The upper wing was significantly enlarged, exceeding 33 feet in span, increasing the total wing area by more than 48 square feet. The ailerons were removed from the lower wing and enlarged on the upper one. Thus, a new modification appeared, differing from the previous pure biplanes, built under a sesquiplane scheme. The search for and installation of engines slightly delayed the commissioning of the first aircraft. Their operation began in the summer of 1915. They were mainly used for pilot training. Overall, the reviews of the aircraft were very positive. It was easy to control, and its flight and technical characteristics fully met the standards of early 1915. Pilots especially noted its good flight speed, up to 89 miles per hour. This was likely achieved during training flights with only 1 pilot on board, since official data stated that at a full load of 496 pounds, the speed reached 78 miles per hour. Its rate of climb was also considered good, 3,280 feet in 4 minutes. The aircraft was inspected by pilots from other aviation units, senior officers of the Russian Imperial Army, members of the royal family, and numerous foreign delegations who visited the squadron of airships to familiarize themselves with the aircraft designed by Igor Ivanovich Sikorsky. The question arose of purchasing the existing aircraft for the state treasury and ordering new machines of the same type. However, replacing the previous order with a new one did not occur. The military department purchased 4 Muromets from the Russo-Baltic Company as compensation for 45 undelivered light Sikorsky aircraft. At the same time, light aircraft were needed to complete the squadron of airships. After several appeals from Mikhail Vladimirovich Shidlovsky on August 11, 1915, the headquarters of the Supreme Commander-in-Chief sent a telegram to the main directorate of the General Staff. It stated that small aircraft were required to perform certain tasks and to train pilots of the squadron of airships. The staff included 12 light airplanes. Some of these machines were already physically present in the squadron, but they belonged to the Russo-Baltic Wagon Building Plant. The pilots requested that most of these airplanes be of the Sikorsky S-16 model. Therefore, they asked to arrange the purchase of the existing machines and the delivery of the remaining ones. Following the relevant request, the main military technical directorate inquired with the Russo-Baltic plant about the conditions. On August 21st, the plant presented its terms for fulfilling the order for 18 S-16 aircraft, 12 for the squadron staff, and 6 more to replace those expected to wear out each month. The Executive Commission of the Special Council for the Defense of the State approved these terms. On October 24, 1915, the main military technical directorate signed a contract with the Russo-Baltic plant for 18 S-16 aircraft equipped with Rhone or Gnome engines rated at 80 or 100 horsepower, as well as 18 main and 3 additional sets of spare parts. The spare part kits included, in essence, all major components of the aircraft. The directorate agreed to pay 9,500 rubles for each aircraft and 4,500 and 7,300 rubles for each spare part kit, respectively. The directorate was also responsible for supplying the engines and propellers for the machines. The delivery schedule was as follows. By October 4th, 1915, 3 aircraft. By November 4th, 4 aircraft and 7 kits. By December 4th, 11 aircraft and 14 kits. The conditions for aircraft acceptance were strict. All expenses for delivery, packaging, and any repairs after breakdowns were to be borne by the factory. The plant was granted an advance payment amounting to 25% of the contract value to set up production. Another 25% was to be allocated for the purchase of necessary materials by the plant. The Aeronautics Department of the Russo-Baltic plant, renamed in May 1915 to the Russo-Baltic Aeronautical Plant, often shortened to Aviabalt, began preparing for production in September 1915. However, not everything went smoothly. Only at the end of the month did the pilots of the squadron of airships prepare their remarks regarding the first prototype S-16 aircraft. Only after this could Igor Ivanovich Sikorsky begin correcting the identified deficiencies in the design of the production machines, which received the designation S-16 serial. They were assigned factory numbers from 201 to 215. Together with the experimental aircraft, they were to make up the 18 machines covered by the contract. In the design of the serial aircraft, Igor Ivanovich Sikorsky introduced a number of small changes compared to the prototypes. The shape of the tail assembly was altered. The wing area was also modified. The wing box of the serial S-16 featured planes of different sizes, similar to one of the prototype models. Aviabalt's production encountered major difficulties due to disruptions in the supply of semi-finished products and components: steel and brass pipes, sheet steel, wheels, bolts, and other parts. Many of these were imported, mainly from Sweden. Because of this, Sikorsky and his assistants had to urgently redesign certain parts and even organize the production of steel pipes at the factory itself. The serial production weight of the S-16 aircraft varied due to modifications, ranging from 916 to 933 pounds. Director of Aviabalt, Mikhail Fedorovich Klimikseyev, took every possible measure to accelerate the construction of the series. Fortunately, in the autumn of 1915, a temporary technological window appeared in the production of the Ilya Muromets airships. All available workers were reassigned to assemble the light aircraft. They worked overtime, including weekends and holidays. However, the strikes that followed one after another nullified all these efforts. By the end of November, it became clear that, at best, only 4 out of the 15 ordered aircraft could be completed on time. The company had to request an extension from the main military technical directorate, which came with a corresponding fine. Only on the 4th of January 1916 did the Aviabalt company finally announce that all 15 serial aircraft were ready for inspection. Yet their delivery was once again delayed. Poor weather interrupted the test flights, which had begun on the 22nd of December 1915, conducted by pilot Georgy Ivanovich Lavrov, who had arrived from the front. During one of the first flights, due to strong gusts of wind, the pilot lost control while landing. The aircraft and its engine were seriously damaged and remained under repair until March of 1916. When Lavrov returned to the front, there were no test pilots left at the factory. Citing the terms of the contract, the military department refused to provide its own pilots. Moreover, the Gnome engines from the military department were also being delivered to the factory with delays. In addition, aircraft deliveries to the Army were hindered by a change in understanding of how they were to be used. An important shift occurred in the history of this aircraft. Its purpose was expanded. If, in mid-1915, this small aircraft had been intended for use within the squadron of airships primarily for training heavy bomber pilots and for reconnaissance during planned raids, then by the end of the year, the idea rose to use them as fighters at combat bases to protect heavy bombers from enemy attacks. According to the newly approved organization of the squadron, it was now planned to have, in addition to 12 training aircraft for the flight school, 14 light aircraft in each combat detachment, 4 fighters, 4 reconnaissance planes, and 6 trainers. The number of combat detachments was also increased from 2 to 3. Like most other reconnaissance scouts of that era, this aircraft evolved into a classic single-seat fighter. Thus, it became the first domestically designed fighter aircraft. The change in the aircraft's role was marked by the development of fixed onboard armament. One of the key advocates for creating a fighter aviation branch in the Russian air fleet was Lieutenant Georgy Ivanovich Lavrov. In 1915, he made several proposals regarding the creation of aviation weaponry and the formation of fighter detachments. In the autumn of that year, he developed and built in the squadron's workshops a prototype of the first Russian synchronizer, a device that allowed automatic firing through the propeller arc. The company received a protective certificate for this synchronizer from the Ministry of Trade and Industry on the 1st of December, 1915. Lavrov's synchronizer, very simple in design, demonstrated satisfactory performance during ground tests and was delivered in December of 1915 to the Aviabalt factory. It was planned to be installed on an aircraft being modified for the Naval Department. After reviewing the synchronizer, the military authorities immediately signed a contract to equip the aircraft under construction with Lavrov's synchronizers. These synchronizers for the serial aircraft were completed only by the 21st of March, 1916, which further delayed the delivery of the planes to the Army. Commander of the airship squadron, Major General Mikhail Vladimirovich Shidlovsky. was in urgent need of fighter aircraft and grew irritated by the delays in their acceptance in Petrograd. Therefore, in the middle of January 1916, he ordered 3 aircraft built in December to be sent to combat units immediately without waiting for official acceptance. The first 2 went to the 1st Combat Detachment in Segewold, now known as Sigulda, and the 3rd to the Southern Combat Detachment of the squadron based in the village of Borkovelska near Ternopil. Their armament was installed directly in the combat units. In January 1916, a high-ranking general at the main military headquarters sent an urgent telegram to the Aviation Administration. He demanded that the delivery of the small S-16 fighter aircraft for the airship squadron be accelerated without delay. Because of the slow acceptance process, 6 aircraft had to be taken before they had even passed official inspection. 2 of these aircraft were already in operation at the bases in Segewold and near Ternopil. 2 more were being used in the flight school to train pilots, and 1 had already been destroyed by a storm. The general insisted if it was impossible to organize acceptance at the factory, the commander of the squadron himself should be authorized to accept the aircraft directly. This protest from the main headquarters truly sped things up. During February and March of 1916, all remaining S-16 aircraft were finally accepted in Petrograd. However, 3 of them had broken engines, delaying their dispatch to the front. Another aircraft was also delayed because it was under repair after an accident at the Avia-Balt plant. 2 fighters were sent to the 1st Combat Detachment in Segewold at the end of March. 2 more were sent to the flight school in Pskov at the beginning of April, and another one followed there at the end of April. 1 aircraft remained at the Avia-Balt plant for a long time and was later converted into an improved modification. The production version of the S-16 was a small, classically designed biplane with a single engine. The engine was mounted in the front, and the cockpit, accommodating 1 or 2 crew members, was open. The fuselage had a framework construction reinforced with wire bracing. The landing gear consisted of 3 supports, 2 main wheels, and a rear skid. The tail assembly was of a conventional type. The wings had a fairly large surface area. The upper wing was larger than the lower one, with a greater span. It was mounted at a slight angle. The aircraft's wings consisted of 2 main structural elements, the front and rear spars. These were hollow, glued box-shaped beams made of Oregon pine and spruce. At the points where the struts were attached, the spars were made solid for added strength. The ribs, the crosswise elements that formed the wing profile, were box-shaped at the points of strut attachment and eye-shaped elsewhere. The upper and lower flanges of the ribs were made of ash, while the webs were made of poplar. The rear edge of the wing was built from an ash plank of trapezoidal cross-section. The wings had a special aerodynamic profile developed by Sikorsky. The entire structure was covered with a fabric skin. For the wings, fuselage, and tail assembly, Russian linen fabric was used, coated with 3 layers of special aviation varnish and emolite. This coating protected the aircraft from moisture and improved aerodynamic performance by reducing air drag. The fabric covering was secured with cord and adhesive. The upper wing was attached to the fuselage with 4 struts and was divided into 2 halves. Each half contained 15 ribs, including the joint ribs. The halves of the lower wing had 10 ribs each. The wingtips were slightly curved upward and backward, a design that improved the aircraft's stability during flight. At the rear, in the central part of the upper wing, a cutout was made up to the rear spar. This improved the pilot's upward visibility. The root sections of the spars had special brass couplings that allowed the wings to be quickly detached from the fuselage when necessary. The distance between the upper and lower wings was about 5 feet, or roughly 1.5 meters. The struts connecting the wings were hollow, milled on a machine, had a streamlined oval cross-section, and were made of Oregon pine. The wing box was braced with steel wires ranging in thickness from 0.06 to 0.1 inch, or from 1.5 to 2.5 millimeters. Each brace wire had a cylindrical turnbuckle to adjust its tension. The turnbuckle was wrapped in oil-soaked paper to protect it from corrosion. The ailerons, which controlled the aircraft's roll, had a relatively large surface area and were located only on the upper wing. They occupied the 9 outer ribs at each wingtip. The front spar of the aileron was made of rounded Oregon pine, allowing it to pivot freely relative to the rear spar of the wing. The trailing edge of the aileron was made of a steel tube to prevent it from deforming during flight. In the middle of each aileron, hollow brass levers were installed to attach the control cables. The fuselage of the aircraft consisted of 4 long beams made of ash or Oregon pine. These beams had a rectangular cross-section that gradually narrowed toward the tail. The beams were connected by struts and crossbars made of ash and spruce. Together, they formed 11 rectangular wooden frames. For additional strength, all joints were reinforced with thin wire ranging from 0.06 to 0.1 inch thick. Each wire had a special cylindrical tensioner wrapped in oiled paper. The wires were fastened to copper and steel clamps that connected the beams with the struts. The front part of the fuselage was a strong steel frame that held the engine mount. The engine was attached to the front of this frame, while the main fuselage beams were bolted to its rear. The front landing gear struts were also fixed to the bottom of this frame. The first wooden frame had the strongest struts and crossbars. It supported the rear part of the engine shaft. In addition, the cockpit floor began from this first frame. The second frame was used for installing cockpit instruments and equipment, including the synchronized machine gun. It also supported the front struts of the upper wing and special fittings for connecting the lower wing. These fittings were copper bushings with slots into which the connecting couplings were inserted and bolted. The point where the lower wings attached to the fuselage was covered with a copper plate. The third and fourth frames were incomplete. They lacked upper crossbars. This was because the crew cockpit was located between the second and fifth frames. The absence of upper crossbars was compensated by additional lower ones that reinforced the floor beneath the pilot's feet. The rear beams of the lower wing and the rear struts of the upper wing were attached to the fourth frame. On the lower crossbars of the fourth and fifth frames, a reserve fuel tank was installed. The undercarriage struts were also attached to the bottom of the fourth frame. Above the tank, on copper pipes, were mounted the seats of the pilot and the navigator. The pilot's front seat was a comfortable chair upholstered with artificial leather, featuring a horsehair cushion and a leather harness belt. The rear seat for the navigator observer, whose presence on this aircraft type was not considered mandatory, was much simpler, a thick felt pad with a strap belt. The navigator sat far less comfortably, pressed against the back of the pilot's seat, practically straddling the fuel tank. The rear semicircular edge of the cockpit was made from a copper tube rim covered with artificial leather. The final, 11th frame served to mount the tail skid and the rear support of the horizontal stabilizer. The fuselage ended with a vertical metal tube that acted as the pivot axis for the rudder. The entire fuselage behind the second wooden frame was covered with linen fabric, fastened with cords and nails. The front part, on the sides and underneath, from the engine frame to the cockpit, was sheathed with plywood. Small access doors were cut into these side panels for engine inspection and maintenance. The space between the engine and the cockpit was covered on top by 2 aluminum cowls. These not only served as hoods over the fuel and oil tanks, but also shielded the cockpit from the oncoming airstream. In addition, a transparent plexiglass windscreen in an aluminum frame was mounted above the rear cowl. On both sides of the cockpit, the fuselage skin featured aluminum stirrups to help the pilots climb inside. At the front of the fuselage, a rotary engine was mounted on a long shaft, topped with a semicircular aluminum hood. The tail section of the aircraft, including the fin, stabilizer, elevators, and rudder, had a framework of thin-walled steel tubes covered with fabric. On some production models, due to a shortage of steel tubing, the frame was made of wood instead. The control surfaces were equipped with hollow brass levers for attaching the control cables. The left and right elevators operated independently from each other. The stabilizer rested atop the fuselage, and each of its halves was supported by 2 tubular struts. The pilot controlled the aircraft using an aluminum control wheel mounted on a column with a chain, which also held the electric switch, and brass foot pedals. To the left and right of the pilot were conveniently placed the engine controls, which included a fuel valve, a throttle lever, and a valve for switching the carburetor to the winter jet. The tachometer was located in the same area. A manual pump for transferring fuel from the lower auxiliary tank to the main one was attached either to the left leg of the pilot's seat or to the left side of the cockpit. Steel control cables from 0.08 to 0.12 inches in diameter ran from the cockpit controls, passing around brass pulleys mounted on ball bearings at the corners. The cables from the wheel and pedals ran inside the fuselage and emerged near the 8th and 9th frames, where they connected to the control levers of the rudders. On the rudder, these levers were located below the stabilizer planes. The aileron control cables ran along the rear spar of the lower wing, then upward through openings in the wing to the aileron lever, which was attached where the rear strut met the rear spar of the upper wing. A small slot was cut in the upper wing to allow the passage of cables and levers. The aircraft's landing gear followed the typical design of Igor Ivanovich Sikorsky's machines from that period. It consisted of two steel tubes with an oval cross-section to reduce drag, tapering into a circular shape at the lower end. These curved tubes, forming the struts and braces, were attached to the fuselage with bolts, allowing the gear to be quickly disassembled. For strength and rigidity, the arches were connected at the bottom by two crossbars and braced to the wings and fuselage with cables. Each landing gear arch supported a tubular steel, or on some aircraft brass, axle carrying two aluminum wheels, 23.6 inches in diameter with rubber tires. In winter, the wheels were replaced by laminated wooden skis reinforced with brass plates. The shock absorber consisted of a rubber cord wrapped several times around the wheel axle and the gear tubes. To maintain the proper alignment perpendicular to the aircraft's axis, the axle was also held by a fork attached with a hinge to each landing gear strut. A wooden tail skid with an aluminum shoe was attached to the fuselage structure by a brass fork and a rubber shock-absorbing cord. According to the technical specifications of the contract, these aircraft were designed to use air-cooled rotary engines, Gnome and Rhone, rated at 80 and 100 horsepower respectively. French Gnome engines were among the most popular in aviation on the eve of the First World War. Their main advantages were low weight, efficient cooling, and fairly high reliability. In 1913, the Gnome Company opened a branch in Moscow, where the following year, they began producing Gnome A engines with a power output of 80 horsepower. At that time, it was one of the best aircraft engines in the world. The 7-cylinder engine weighed 207 pounds without oil and fuel and produced between 70 and 75 horsepower. However, it had several problems: imperfect carburetors, poorly placed intake valves on the pistons, and limited power regulation. Pilots sometimes had to temporarily shut down the engine in flight. Fuel consumption was very high, over 330 grams per horsepower per hour, and oil consumption exceeded 130 grams. Before a major overhaul, the engine could operate for no more than 20 hours, and after repairs, its characteristics, especially power, deteriorated noticeably. Less powerful versions, the Gnome 70 and Gnome 50, used on training aircraft, never actually produced more than 60 and 45 horsepower respectively, despite the claimed figures. By the end of 1915, the engine's power was already insufficient for combat aircraft, but it remained the only rotary engine produced in large quantities in Russia. With the appearance in 1914 of more powerful serial engines, the Rhone 80 and Gnome monosupape, the Gnome A was considered obsolete. Production of the domestic rotary engine Calep 80 with 85 horsepower, a weight of 192 pounds, and a guaranteed service life of over 50 hours, which far surpassed the Gnome A in performance and reliability, was halted after the evacuation of the Riga motor plant. An excellent replacement for the outdated Gnome A was the French 9-cylinder rotary Rhone 80 engine, supplied to Russia under Allied agreements. It was also planned for production in Moscow. The engine produced 80 horsepower, weighed 260 pounds, had a much better and more reliable design, and consumed less fuel, between 270 and 300 grams per horsepower per hour, and less oil, around 50 grams. This modification's power reached 90 horsepower, and later versions produced 110 and 120 horsepower. However, expectations for regular Rhone deliveries were not fulfilled. One of the Rhone 80 engines was requisitioned by order of Grand Duke Alexander Mikhailovich from the Lebedev aircraft plant, where it had been kept specifically for testing experimental aircraft. After an accident, this Rhone was returned to the plant. The 9-cylinder rotary Gnome monosupape 100 engine was developed in 1913. The name monosupape, meaning single valve, reflected its key design feature, combining the intake and exhaust functions in one valve. The engine produced 100 horsepower and weighed 298 pounds. In the monosupape, many of the design flaws of its predecessor, the Gnome A, were eliminated. Fuel consumption was reduced to 300 grams per horsepower per hour and oil consumption to 110 grams. The Moscow branch of the Gnome Company attempted to establish mass production of monosoupape engines, but success came only gradually. By 1915, the engine was considered scarce, as was the Rhone 80. The fuel and lubrication systems consisted of an oil tank, main and reserve fuel tanks, pipelines, and both feed and transfer pumps. The full fuel supply allowed for flights lasting 3.5 hours. The main fuel tank and oil tank were mounted above the upper fuselage longuron in front of the pilot's cockpit. They had a semi-cylindrical shape, were made of brass with a thickness of 0.03 inches, and were secured to the longerons with leather straps, the oil tank in front and the fuel tank behind. The latter featured transparent windows that allowed the pilot to monitor the fuel level from the cockpit. The spare fuel tank was made of brass and was located directly under the pilot's seats. There was a filler neck with a filter at the rear of it and a special device that allowed fuel to be pumped into the main tank. All oil and fuel lines were made of copper. These aircraft used wooden, two-bladed propellers of various types from different factories. On the first experimental examples, there were propellers of the system developed by Nikolai Yegorovich Zhukovsky, manufactured by the Moscow Aerotechnical Plant. For production machines, propellers of the French integral type were ordered, produced by the Petrograd plant of Vladimir Alexandrovich Lebedev. Because of confusion in the engine documentation, propellers were made with different diameter-to-pitch ratios: 100 by 81 inches, 100 by 85 inches, 100 by 71 inches, and 98 by 77 inches. Later in the summer of 1916, the Avia-Balt plant established its own production of Sikorsky-type propellers, with a ratio of 100 by 71 inches. Aircraft with the Gnome monosoupape engine were fitted with propellers 102 by 91 inches. This airplane became the first fighter in Russia, and one of the first in the world capable of firing through a rotating propeller thanks to a special device, the synchronizer. It was developed in 1915 by Lieutenant Georgy Ivanovich Lavrov. In mid-November of that same year, the device was tested at the firing range of the Pavlov Military School in Petrograd, after which the Avia-Balt plant received an order for serial production. For each synchronizer, the plant received 1,000 rubles. It was also planned to install these devices on other types of aircraft. The Vickers machine gun was placed to the left of the pilot's seat, directly on the engine cowling. A trough for the cartridge belt ran along the outside of the fuselage. The ammo drum with the belt stood by the pilot's feet. The gun's trigger mechanism was connected by a system of levers to an eccentric that was turned by a worm gear. The worm was mounted on the end of a long steel rod, and the other end, through a universal joint, was connected to the shaft of the engine's oil pump. The pump was driven by the engine's rotation through a system of gears. The eccentric, periodically pressing on the levers, regulated the rate of fire of the machine gun. This ensured synchronization. Either the pilot himself or the observer seated behind him could fire. At the firing range, they tested the Vickers installation with Ron and Gnome engines. Even then, it became apparent that adjusting the eccentric and the whole system was rather complicated. But because no other synchronizers were available, Lavrov's device was installed on production aircraft. In January of 1916, the Avia-Balt plant adapted Lavrov's synchronizer for the Colt machine gun, which was more common in Russia. Because of the design features, this gun was mounted to the right of the pilot's seat. A lightened modification of the Russian Maxim was never realized. During use, Lavrov synchronizers proved insufficiently reliable. The universal joint and the worm connection constantly broke. The mechanism's settings were disturbed and had to be restored after every flight. When the engine ran at low revolutions, synchronization failed and firing became impossible. Reliability was further reduced because the guns were not rigidly attached to the fuselage's primary structure. As a result, the gun and the entire system vibrated heavily in flight. Refinement of the synchronizer continued at the Avia-Balt plant up to 1917, since its improved version was planned for installation on new fighters. In the summer of 1916, Soviet designers encountered reliability problems with the synchronizer for machine guns. This part constantly broke and required refinement. Therefore, other armament options had to be sought for the S-16 aircraft. On several machines, the synchronized Vickers guns were replaced with Colts, and possibly with Lewis's. These were installed above the central part of the upper wing. The cartridge belts and the boxes for spent shell casings were placed to the sides of the guns in streamlined housings so as not to create unnecessary air resistance. By the middle of 1917, all armament was removed from the remaining S-16 aircraft. After that, they were used exclusively for pilot training. Besides the fixed, heavy machine gun that fired forward, it was planned from the beginning to give the second crew member, the pilot observer, his own armament. For this purpose, the handheld Madsen machine guns, of which the airship squadron had many at its disposal, were most often used. The observer fired them by hand, to the side and to the rear of the aircraft. Instead of the Madsen, the pilot observers could be armed with other weapons, the Russian three-line carbine model 1907 or the Austrian cavalry carbine model 1895. And in 1917, it became possible to use an automatic rifle or the Fedorov automatic, as well as a Winchester hunting carbine with automatic action. In addition, each aircraft carried a Mauser pistol on board. The leadership of the airship squadron also planned to equip the S-16 with bombs as well as machine guns. In connection with this, at the Avia-Balt factory in April 1916, they manufactured a batch of 49 2-pound bombs, weighing 1.8 pounds each.